Hi everyone, Rhoda here with another JAC capsule. This one is a solution to all of the trigonometry exercises that are posted. This is going to be a long video because I'm going to go through the entire document here, but if you look below, you'll find timestamps. If you want to jump ahead to specific questions, that'll all be indicated there. So first question is asking you to find a bunch of different trigonometric values. I posted a video showing you how to get the values for sine and cosine. When you're asked to find values other than sine and cosine, that's fine. You're just going to take that trigonometric function, whatever it might be, and remember how to express it in terms of sine and cosine. And if you take a look at the notes that are posted in PDF form, you have this recap there where you can find these relationships that we're going to be using. So I'll just write them up here for when we need them. But the main thing is to go back to what we learned about the unit circle. So number 1a, we want sine of pi over 3. The first thing to do is remember that pi over 3 can be written as 2 pi over 6. So I'm looking at a multiple of pi over 6 on my unit circle. That means I can divide each half of the circle into 6 equal portions, and each portion would then be worth pi over 6. So I just count 0, 1 pi over 6, 2 pi over 6 is right here. And I'm just drawing this triangle because I need to think about what's bigger, x or y. I'm looking for sine. Sine is the y value. That would be the height. Compare that to the width, which would be the x value. I can see that the y value is the bigger number. That means that it's going to be root 3 over 2. Now I need to know, is it positive or negative? Well, here my y value would be above the x-axis, so it's positive. So the final answer is root 3 over 2. That's the value of sine of pi over 3. Moving on to the next one, in part B, we want to know what is sine of we want to know what is cosecant of negative 5 pi over 6. So in order to get cosecant, we need to know what is cosecant in terms of sine and cosine. So I've written that up here on the right. So cosecant is 1 over sine. That means I'll start by just finding what is sine of negative 5 pi over 6. Again, it's a multiple of pi over 6. It's negative, so I'm going to be counting clockwise instead of counterclockwise. So starting at 0, divide into 6 even wedges and count. 1, 2, 3, 4, 5. Negative 5 pi over 6 is down here. So sine is again the y value. If I look at the x compared to the y, I can see that this time y would be the smaller number, which means it is 1/2. But is it positive or negative 1/2? If I look at the y value again, since it's below the x-axis, I know that it's negative. So sine of negative 5 pi over 6 is negative 1/2. Finally, I wanted cosecant. I didn't want sine. So cosecant is 1 over sine. That means that my answer is 1 over negative 1/2, which you can, of course, rewrite as negative 2. Let's keep going. Cotan. Again, I need to know what is cotan in terms of sine and cosine. Well, cotan is, by the way, cotan is 1 over tan. That's another identity that's good to know. This way, if you remember that tan is sine over cosine, you would know that for cotan, you flip it the other way around. Cotan is cosine over sine. So for pi over 2, I'm going to need to figure out what is the value of cosine and what is the value of sine. Pi over 2, let's find it on the unit circle. I know that the top half of the circle is worth pi radians. So if I cut it into 2 even sections, then each one would be worth pi over 2. So 1 pi over 2 would be right up here. Now, this is a unit circle. It has radius 1. So I know that the y value here is going to be 1. The x value, since I'm on the y-axis, is going to be 0. So cosine would be the x value at that point, which is 0. Sine would be 1. That means that cotan at pi over 2 is 0 divided by 1, which is just 0. Next one. Okay, this time we want a multiple of pi over 4. We're asking for cosine of 9 pi over 4. So divide the top and bottom halves into 4 wedges each. That means each one is worth pi on 4. So 0, 1 pi on 4, 2 pi on 4, 3, 4, 5, 6, 7, 8 pi on 4 brings me around to where I started. And I need to keep going one more. So if I keep going, I get 9 pi on 4 is in the same spot as 1 pi on 4. So for multiples of pi on 4 at these diagonal positions, I know that the answer is going to be root 2 over 2. I just need to check, is it going to be positive or negative? Cosine is the x value. And in this position, I can see that x would have to be positive since it's to the right of the y-axis. So it's just root 2 over 2. Next, we have tan of 5 pi over 3. So again, for tan, we need to break that down into sine and cosine. So we need to know tan is equal to sine divided by cosine. The angle in question is 5 pi over 3. I will convert that into 10 pi over 6. So that I can use my method for multiples of pi on 6. So we divide each half into 6 wedges. And we count around. So 0, 1, 2, 3, 4, 5, whoops. Let me do that again. Sorry, I'm going too fast. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi on 6, or in other words, 5 pi on 3 is right here. By the way, I went too fast and I made a mistake a second ago. Something I could do to avoid mistakes is to jump ahead a little bit. So I could have said to myself that this is pi right here and pi is 6 pi on 6. So I could have started counting from there just to make it a little bit easier and maybe less likely to make a mistake. But it doesn't matter. In the end, I got to the right spot. So now look at the x value and the y value. Here I can see that y is going to be the bigger one. So sine, my y value, would be the larger number, which is root 3 over 2. And I can see that sine is going to be negative because it's below the x-axis. So negative root 3 on 2. Cosine would be the smaller value, which is 1/2. And in this position, x is positive, so it's just positive 1/2. Now I can take those two and put them together. Tan would be the sine value divided by the cosine value. To clean that up, I could notice that since they're both divided by 2, why don't I multiply top and bottom both by 2 to get negative root 3 over 1, or just negative root 3 for my final answer. Great. Now the last one is the trickiest one. I'm asking you to do a bunch of stuff here because that's what you're going to see in real problems. You're going to end up having to evaluate functions as specific values, and there's going to be some cleanup. So this is not only about knowing your trig values. Here you also have to have some computational skills, a little bit of algebra. But we'll start by getting those trig values. So what do I need? I need sine of 5 pi on 4. I need secant of pi on 3. So for this one, I'm going to need to know that secant is equal to 1 over cosine. And then I need cosecant of pi on 3. To get that, I'll need to know that cosecant is 1 over sine. So I've got 3 things that I need, basically. I need sine of 5 pi on 4. I need cosine of pi on 3. And I need sine of pi on 3. Let's start with 5 pi on 4. That's a multiple of pi on 4. So we're going to break the top and bottom into 4 equal regions. And we're going to count. 0, 1, 2, 3, 4, 5. 5 pi on 4 is right here. I know that the answer would be plus or minus root 2 over 2. Here I can see that the y value would be negative because we're below the x-axis. That means that's the sine value would be negative. So I've got my value for sine. The next 2 angles that I need are pi on 3, which I can rewrite as 2 pi on 6. So that's a multiple of pi on 6. 2 pi on 6 would be up here. Here I can see that in this position, the x value would be the smaller number, so 1/2. The y value would be the larger number, so root 3 over 2. And I'm in the first quadrant, so they both would be positive. So now I have all of the trig values that I need. Now I need to use those to evaluate my bigger expression. So before I do that, let me just remind you of something really important. When you see something like sine cubed of 5 pi on 4, this cubed here that's inside of the sine, well, that's just a compressed notation. We write it that way to save space, but it really means sine of 5 pi on 4 all to the power of 3. And when you're evaluating it, you need to think about it that way. So when we put the 3 in the middle there, it happens with sine, cosine, any trig function, and it happens with a couple other functions you might see later too. It's really just there as a convenience. It's annoying to write sine all to the power of 3 like I did the second way. So we just stick it in there to save space. But when you're actually doing math, you need to remember that it's actually equal to this thing on the right-hand side. So when I'm evaluating, I'll need to write it like that. Same goes for secant squared and cosecant squared. Those squares there really belong over the whole entire expression. So if I was going to write it out more clearly, it would look like this. And you'll notice I changed a bracket to a square bracket. I only did that to make it a bit more clear which bracket is which, because when we do use this bigger notation, there's so many brackets everywhere that it can be hard to follow, which is why we have the compressed notation to make it look better most of the time. But if I write it out like this, then we're less likely to make a mistake when we're evaluating. So now let me replace sine of 5 pi on 4 is negative root 2 over 2. Secant of pi on 3 is 1 over cosine of pi on 3. So it's 1 over 1/2. Cosecant of pi on 3 is 1 over sine of pi on 3. So it's 1 over root 3 over 2. Now we need to evaluate this. So I'm going to do a few things here. The first thing I want to do is deal with these fractions inside of fractions. I always try to get rid of those first when I have them. I have 1 divided by 1/2. I can flip the denominator there, so that's just going to become 2 inside the square. And then next one I have 1 over root 3 over 2. So again, I can take the reciprocal, so that's 2 over root 3. Now I will deal with the exponents. So when I exponentiate a fraction, remember that that exponent goes to the numerator and to the denominator. So negative root 2 cubed. I'll deal with that in a sec. In the denominator, 2 cubed, well, that's just 8, so I'll write that down. Now I have 2 squared is 4, and then my next fraction, again, I square the top and the bottom, so 2 squared becomes 4, square root of 3 squared becomes 3. Okay, I haven't cubed the negative root 2 yet, because I wanted to just show you how I would think about that. So negative root 2 cubed is negative root 2 times itself 3 times. 2 of those I could put together to get 2. So I can think of this as negative root 2 all squared, and then there's an extra 1 left over. So because of that, I'm going to write this as negative root 2 times 2. And that's still divided by 8. Now I notice that I can reduce that because I have a times 2 on top, which I can reduce with the 8 from the bottom. And then in my square bracket, I have 4 minus 4/3. So I will want to combine that into a single fraction. To do that, I can rewrite the 4 as 4 times 3 over 3 in order to combine them. So that becomes 12 minus 4, all of that divided by 3. Just going to calculate that. So I have 8 divided by 3 now. So now I have a product of 2 fractions. And again, I can reduce. I have an 8 in the numerator, which divided by 4 here would give me 2. I can put that all together into one fraction. And that's as far as I can go. The one thing that I would change here is it's just going to be a little bit confusing the way I've written it. When you have a square root in a product, I would always put it last. So it's much better to write it as negative 2 times the square root of 2. This is just less confusing. I'm not going to make a typo in the next line and accidentally write the square root of 22 or anything like that. So this is what I would propose as the best way to write your final answer. On to number 2. In number 2, it's a little bit of a different thing. This is to do with SOH CAH TOA. So let me give you a little reminder of that. SOH CAH TOA is just a shorthand to help us remember how to relate sine, cosine, and tan to the values of a right angled triangle, the sides. So sine is the opposite side divided by the hypotenuse. That's SOH. Cosine is the length of the adjacent side divided by the hypotenuse. That's CAH. Tan is the opposite side divided by the adjacent side. That's TOA. So you'll see those in action in this problem. But the first thing I need to do in this problem actually, well, I should read the question. So given the following right triangle, I see I have this triangle here. I have the lengths of 2 sides and I want the missing one. So part A, find the length of the missing side. Well, that's not anything to do with SOH CAH TOA. That's all about Pythagoras. So since I have a right angle triangle, I can use the Pythagorean theorem. If I call this missing side H for hypotenuse, then the Pythagorean theorem says that the 2 legs, their lengths squared, or O and A, if you want to think about it that way, adds up to the length of the hypotenuse squared. So if I calculate that out, I have 9 plus 25 is equal to the length of the hypotenuse squared. I can take the square root on both sides. Normally when you take the square root on both sides, there would be a plus or minus. But here I know the hypotenuse has to be a positive number because you can't have a negative length. So that's why the answer is just square root of 34. So now I know the length of this side is square root of 34. Now that we know the value of H, we can find the rest. So in part B, they want you to find cotan of alpha. So if alpha is the angle in question, then that's the perspective that we're looking from when I talk about the opposite or the adjacent side. So if I start here looking at alpha, the opposite side is the one that's opposite from that angle. So this would be my O, and the adjacent side is the one that's adjacent to that angle. So this would be my A. So now I can find cotan. I know that tan would be opposite over adjacent. Cotan, remember, is the reciprocal of tan. So if tan is O over A, that means cotan has to be A over O. So it's the adjacent side length divided by the opposite side length, which would be 3 over 5. And that's all there is to it. So same thing for C. This time we want secant of beta. If beta is the angle in question, that's my perspective. So starting from beta, the opposite side is the one across from beta. So that's the one that measures length 3. The adjacent side is the one adjacent to beta. So that's the one that has length 5. Okay, now secant is 1 over cos. And we know that cos is equal to the adjacent over the hypotenuse. That's the CAH from SOH CAH TOA. So if cos is A over H, then secant would be the reciprocal, H over A. Now H is what we found in part A, it's root 34. A would be, in this context, 5. So there you go. That's how you can find the trig values, sine, cosine, tan, secant, cotan, cosecant, all 6 of them from just having the lengths of the sides of a right angled triangle. So that brings me to number 3. And number 3, we could solve it 2 different ways. We could solve this one using the method that I just explained with the triangle, or you could do it with your trig identities if you know those quite well. So in number 3, they don't give you a triangle, but they tell you that for this particular angle, cosine is equal to 1 over 5. And then based on that, how can we find some other values? Sine, secant, and tan. So I'll do these side by side. And I'll show you 2 ways to do it. First way would be to use that triangle that we were just talking about. If I know that cosine is equal to 1 over 5, and I know that for a right angled triangle with angle theta, cosine would be equal to the length of the adjacent side times the length of the hypotenuse. So I could make kind of a model triangle for this situation. 1 over 5 would come from the adjacent over the hypotenuse. So I could put those values in. I could make a triangle where the length of the adjacent side is 1 and the length of the hypotenuse is 5. How would that help me find sine? Well, I know that sine of that same angle would be the opposite over the hypotenuse. And then I could use the Pythagorean theorem to solve for the length of the opposite side. So I could say that means that the length of the opposite side has to be the square root of 5 squared minus 1 squared, which is the square root of 24. Or we can clean that up by noticing that it's the square root of 4 times 6, and the square root of 4 is 2, so we could say this is 2 root 6, just to make it a nicer answer. So this would be the length of the opposite side. Now sine is O over H, O is 2 over root 6, and H is 5. So now I have the value of sine. That's one way to do it. And that method will be quite important when you get to Cal 2. But another way to do it would be to use your Pythagorean theorem. So I know that from the Pythagorean theorem, I can get this identity here. Sine squared plus cos squared is equal to 1. Now another way to write that is sine squared is equal to 1 minus cos squared. So I know that cosine of theta is equal to 1 over 5. I could plug that in the place of cosine, and that gets squared. So that means that sine squared is equal to 1 minus 1 over 25. In other words, sine all squared is equal to 24 over 25. Now I can take a square root. And I get my answer. which again, I could clean up. I'm taking the square root of the top and bottom individually. And if I tidy up the numerator, I get the same answer as before. For the other two problems, I can, again, choose one of these two options. The first option is to work off of a triangle, and the second option is to use my trig identities. Now, I should just mention something. There was actually a typo in the original question. I didn't include this part originally, and that's very important. So the reason why this is working is because in the question, we know that the angle is between 0 and pi over 2. Why is that important? Well, it tells us that sine and cosine are both positive. So just so you know, if I didn't have that part of the question, I could still find sine, tan, cotan, whatever I need using this triangle method, but I wouldn't know if my answer should be positive or if it should be negative. That would depend on what quadrant my angle is actually in. And you can see that when you do option 2, because when I took the square root here in part A, you know, when you take a square root on both sides, you should have a plus or minus. So the reason why I didn't include that plus or minus was because I know that my angle is in the first quadrant from the question. So I know that sine and cosine are both positive. Just mentioning that in case you run into other questions in the future. So for part B, again, my first option would be to refer to this triangle that I've developed that represents the situation I've been given. So in this triangle, I've already found the lengths of all three sides. I was saying theta would be this angle here. So when I want secant theta, I could say, well, if cosine is a over h, then secant is the reciprocal, it's h over a. So 5 over 1, so it's 5. In this one, option 2 is quite a bit more straightforward. Option 2 is to use your identities, then you don't need a triangle. Well, I know that secant is 1 over cosine, and cosine is the value that the question gave me to begin with. So I could just say that it's 1 over 5. So of course, it's 5. On to part C. This time we want tan. So option 1 would be to build this triangle, find the missing side, but we've already done that. And then use SOH CAH TOA to get the value that you're looking for. Tan of theta would be O over H. O we already found was 2 over root 6. Sorry, I said O over H. O over A is what I meant to say. Tan is O over A, so it's 2 over root 6 over 1, or just 2 over root 6. To do this using identities, well, our basic Pythagorean identity is this one, sine squared plus cos squared equals 1. There are two other versions of this identity. I hadn't mentioned them yet, but hopefully you've seen them before. If you haven't seen them before, no big deal. You just build them from this one. So when you have sine squared plus cos squared equals 1, there's two things you could do to get a new identity. One is divide everything by sine squared. If I do that, what happens? Well, sine squared over sine squared gives me 1. Cos squared over sine squared, cos over sine is cotan, so I get cotan squared. And 1 over sine is cosecant, so I get cosecant squared. So this gives me a whole new identity, which is a good one to know, and you're going to need to know it, especially in Cal 2. Other thing I could do, let me erase this. Instead of dividing by sine squared everywhere, I could have divided by cos squared everywhere. In that case, I get sine squared over cos squared. Well, sine over cos is tan, so it's tan squared. Cos squared over cos squared is, of course, 1. And then 1 over cos squared is secant squared. So then I get this other identity right here. So that would be one way to do it. I could work from this identity. Tan squared plus 1 is equal to secant squared. The value that the question gave me was cosine. So then I would say secant squared is 1 over cosine squared. Cosine I can fill in as 1 over 5. And I can move that plus 1 to the other side. So then tan squared is equal to, well, okay, 1 over 5 is 1 over 25. And then that's all in the denominator. So this first expression, if you work it out, comes out to 25. So now I get tan squared is equal to 25 minus 1, so 24. And then I can take the square root on both sides. Normally, you get a plus and or a minus there. But again, we know sine and cosine are both positive. So we can just take the positive case. And then lastly, we could always clean that up like we did in part A by noticing that this is 4 times 6, and we can square root the 4. So there you go. That's 2 different ways in general of finding another trig value based on one that you already know. That's a skill that's going to come up here and there in Cal 1 and again in Cal 2. All right, so now in number 4, it's all about those trigonometric identities that you have the option to use in question 3. So here we really need to know our Pythagorean identity, that's sine squared plus cos squared equals 1. And then we need to know how to write cotan, secant, and cosecant, all in terms of sine and cosine. If you need a refresher on that, you can find it at the top of this page over here. So we're going to need these. Let's go back down. Great. So first one, I have cotan times cosecant. Well, I don't necessarily know where this is going, but I know that in order to try and clean it up, I need to rewrite these in terms of sine and cosine. So cotan is the same thing as cosine over sine. Secant is the same thing as 1 over cosine. Okay, so that's simple enough. I can reduce this. Cosine divided by cosine would be equal to 1. Or you could say it cancels out, leaving you only with 1 over sine. There is a catch here. Whenever you divide by something that you don't know the value of, you need to consider, what if I just divided by 0? So in the situation where cosine is equal to 0, then this would make no sense. So I'm going to say that it can be reduced to 1 over sine if cosine is not equal to 0. In the case where cosine is equal to 0, then this expression is just undefined. And then finally, 1 over sine, I know I can write a little bit more neatly as cosecant. So my answer would be that this is the same thing as cosecant, but only in the situation where cosine is not equal to 0. That's what allows me to cancel it out. In B, I'll do the same thing. I'll rewrite tan as sine over cosine. And then cosine I'll leave as it is because I see that again, I can say that cosine divided by cosine would be equal to 1. So it cancels out, you could say, leaving you with only sine theta. But I should specify that this is only going to work if cosine of theta is not equal to 0. Because if cosine of theta is equal to 0, then this expression doesn't give me sine. It gives me an undefined expression. So that's an important thing to keep track of. In the next one, I see I have sine squared and I see I have cosine squared. So that's a hint that I'm going to be using my Pythagorean identity. 1 minus sine squared is equal to cosine squared. So that whole numerator becomes cosine squared. This is just coming from sine squared plus cos squared equals 1, which you can also write as cos squared equals 1 minus sine squared, or as sine squared equals 1 minus cos squared. So you need to get good at recognizing sine squared plus cos squared, 1 minus sine squared, and 1 minus cos squared. You need to pick those out of expressions because when you notice those, then you can clean them up into something nicer and move forward in your problem. So here I noticed right away my 1 minus sine squared. I'm really trained to notice that, and you should be too. So I replace that right away. And then same thing, I see 1 minus cos squared in the denominator. That tips me off immediately. I'm going to replace that with sine squared. So this is cos all squared over sine all squared, which I could group as cos over sine. Both of them are squared, so I could write it like this. And then cos over sine is cotan. So it's cotan all squared, which we can just write in that compressed notation for convenience of cotan squared of x. These two lines mean the exact same thing, but we usually use that tidier notation when we give our final answer. All right, next one. Cotan of y times tan of y. Well, you could approach this on a couple different ways. You could say cotan is 1 over tan. I'm going to just write it as cotan is cos over sine, and tan is sine over cosine. If I do that, then I would say, oh, okay, well, here I'm doing cosine divided by cosine, that's equal to 1. Here I'm doing sine divided by sine, that's equal to 1. Everything cancels out, as we say, leaving you just 1. But remember, there's a catch, right? So if I take any angle y and I multiply cotan of that angle times tan of that angle, this is claiming that it's going to give me 1. Well, that's true unless it's undefined to begin with. So it's not true if this was giving me a division by 0. Then I can't cancel out. So it's not true if sine of y is equal to 0. And it's not true if cos of y is equal to 0. But the rest of the time it would work. It's just good to keep those things in mind. So anytime you divide by an unknown, keep in mind that there's the situation where you just divided by 0 and you need to kind of remove that from your set of possible answers or consider it on its own. Last one. I have secant times sine squared all over 1 plus secant. Okay, well, there's nothing obvious here for me to do right away, so I'll do the only thing I can, which is take my secants and rewrite them as 1 over cosine. So I have 1 over cosine instead of secant, multiplied by sine squared on top, and that's divided by 1 plus 1 over cosine. Now me, I don't like fractions within fractions. So if I see that I have a fraction inside of a fraction, I immediately try to get rid of it. How would I get rid of it here? Well, my common denominator is cosine. I'm going to multiply everything by cosine to get rid of those extra fractions. So my whole numerator gets multiplied by cosine, and my whole denominator gets multiplied by cosine. In the denominator, it would distribute. So each term gets multiplied by cosine. I'll write what that gives. So in the denominator, I would get 1 times cosine is cosine. And then 1 over cosine times cosine is 1. And maybe you're thinking of the canceling out thing here. That's if cosine is not equal to 0. I'll worry about that a bit later. On the top, I multiplied the whole thing by cosine. But instead of it being 2 terms on the top, I don't have a plus or a minus on the top. The numerator of my original expression is 1 term. A term is something that you add together or subtract. So here it's all one thing. When I multiply it in, it does not distribute. So I choose, am I going to multiply it onto the sine or am I going to multiply it onto the cosine? I don't do it to both. So I'm just going to bring it into this bracket here. This way it cancels out. And I just have sine squared. I'll make a little note here that this works if I didn't just divide by 0. Sometimes these little notes aren't important because you're catching cases that wouldn't have made sense for the problem anyway, but I just want to practice some good habits, so I'm writing them down. All right, so now I have a simpler expression, sine squared over cosine plus 1. This one has a tricky final solution. So I know that sine squared is equal to 1 minus cosine squared. Why would I do that though? So replacing sine squared with 1 minus cosine squared is allowed. It doesn't look like it would be helpful, but what I'm noticing is that the denominator here, cos plus 1 or 1 plus cos, would be one of the two factors that I would get from factoring 1 minus cos squared. So this is a tricky trick. I'm just showing you because you'll see it sometimes in calculus. That another thing to keep in mind is that these important expressions, remember up here I said that these guys were important to know, 1 minus sine squared and 1 minus cos squared, those are differences of squares. So you can factor that. So if I factor my numerator, I get 1 minus cos times 1 plus cos. And 1 plus cosine is the same thing that I have in the denominator. So now I can reduce even further. I can say 1 plus cosine divided by 1 plus cosine is equal to 1, or you could say they cancel out. And you're just left with 1 minus cosine of theta. But that's only valid if I didn't just divide by 0. Okay, so I have two kind of conditions here. I have my solution only makes sense if 1 plus cosine is not 0. And my solution only makes sense if cosine is not 0, because those are the two times that I divided by something that could be 0. So maybe what I should actually say is that my original expression from E is the same as 1 minus cos theta, unless 1 plus cos theta is equal to 0, or unless cos theta is equal to 0. But as long as those two things are not true, then this is equivalent to my original expression. All right, now we come to the trickiest part of this worksheet, number 5. Here we have to work backwards. So instead of me giving you an angle and you giving me sine or cosine of that angle, we're giving you cosine or sine is equal to something, and you should tell me what the angle is. Or almost, before you even can do that, first you have to solve a little equation. So in A here, the first thing you need to do is figure out if this equation is true, what does that tell you about the value of cosine? In other words, isolate cosine in this expression. So I can do that. I'm going to start by moving the plus 2 to the other side. 1 minus 2 will be -1, and then I'm going to divide both sides by 2. So this equation tells me that cosine has to be equal to -1/2. I have to figure out at which angles does that happen. So we basically take the strategy we learned for the unit circle and we apply it backwards. So cosine is the x value. X has to be negative, and it has to be the smaller of those two numbers that we get for multiples of pi on 6. So we know for multiples of pi on 6, the values are always 1/2 or √3 on 2. 1/2 is the smaller of those. So x is going to be the smaller value, and it's on the negative side. So the angle would be sort of here. Or we could drop it down and get the same x value underneath. So these are the two positions on my unit circle for which x would be equal to -1/2. I know that these come from multiples of pi over 6. So what I can do now is separate it into 6 wedges on the top and the bottom. I know my picture is not the best, but it gives us the main idea. And now we count to figure out which angles are those. So starting at 0, I can go 0, 1, 2, 3, 4, 5, 6, 7, 8. So that means that cosine is equal to -1/2 at the angle 4 pi on 6, which is 2 pi on 3, and at the angle 8 pi on 6, which is 4 pi on 3. Of course, those aren't the only ways to get to those positions. I could keep counting. I could go, okay, I did 1, 2, 3, 4, 5, 6, 7, 8. Let's keep going. 9, 10, 11, 12, 13, 14, 15, 16. So 4 pi on 6. Another way to get to that same point on the unit circle would be 16 pi on 6. Or instead of counting around, basically what I did is I added a full turn, so I added 2 pi. 2 pi you could think of as 12 pi on 6. So if I add 12 pi on 6 to either of these, for example, if I do 8 pi on 6 plus 12 pi on 6, I would get another angle that has that same cosine value. That's why in the question, they told you what region they're interested in. Here, they're only interested in answers from 0 to 2 pi. In other words, just one regular counterclockwise turn around the circle. That means I can scratch all this green stuff out. And the 2 answers that I found are the only answers that they're looking for, because those are the ones in one turn of the circle. So I get that x has to be 2 pi on 3 or 4 pi on 3. This is the basic technique that you're going to use for all of these problems, although there are some extra tricks thrown in here and there for the others. So in B, same idea. I only have one trig function here, sine of x. I'll start by isolating that. So all I need to do is divide the 6 to the other side. Okay, but this time it's not a trig value that I recognize from my circle. So that's the extra trick that's thrown in here. I'm not going to give up. I'm pretty sure that I would not be asked this question unless it was something I could solve based on my knowledge of the unit circle. So let me see if I can simplify this a little bit. The square root of 18 is the same thing as the square root of 9 times 2. So I could separate that into 2 individual square roots. I can square root the 9 and the 2 separately. Square root of 9 is 3, so I get 3 root 2 over 6. And then I can reduce that. 3 divided by 6 gives me 2. So actually, this is asking me for sine to be equal to root 2 over 2. Aha, I do recognize root 2 over 2. That's from my multiples of pi over 4 unit circle. So that's when we go straight through the middle at a diagonal. I know that this one here would be 1 pi over 4. Now, sine has to be root 2 over 2. So sine has to be positive. That would happen here. Or I can get the exact same sine value if I go across to here, which would be at 3 pi over 4. I did that a bit quickly, but again, you can get it by counting around the circle. So on the region from 0 to 2 pi, that's one regular full turn around the circle. There's 2 spots where y would be equal to root 2 over 2. Those are the answers we're looking for. So x can equal pi over 4 or 3 pi over 4 to make this equation true. They're going to get a little bit trickier from here. We're going to have some more complicated functions to work with. In C, I have both sine and cosine. So what can I do? Well, first I'll just try cleaning it up a little bit. I see I have a 1 on both sides. So if I subtract 1 from the left and from the right hand side, I would have sine of x is equal to negative cosine of x. Now, if you know your unit circle well, maybe you can just leave it at this, because you know that there are spots where sine and cosine have the same numerical value, but they're not the same sign. The only spots on the unit circle where sine and cosine have the same kind of size, you could say, is the root 2 over 2 case, those diagonals from the pi over 4. So based on that, I could get an answer right away. Or if you want, you could divide both sides here by cosine. And then you could say that tan of x has to equal negative 1. So that would be another way for us to ask you the question. But the solution would be the same. For tan of x to be negative 1, you would say, well, that means that sine divided by cosine is equal to negative 1. That means that sine and cosine are the same number, but opposite sign from each other. So on the unit circle, where does that happen? To be the same number, they have to both be root 2 over 2. To be the same number but opposite sign, either x is positive, y is negative, or the reverse. So if x is positive and y is negative, then we're down here in the fourth quadrant. Or if x is negative, y is positive, we're over here in the second quadrant. So what are those positions? Well, I can count 0, 1, 2, 3. This is 3 pi over 4. 4, 5, 6, 7. So that's 7 pi over 4. So in the one full turn of the circle, I get two positions for which tan is equal to -1, or in other words, for which sine and cosine are the same number, but opposite signs. So my answer, x is 3 pi over 4, or 7 pi over 4. Let's keep going. Okay, now we're going to throw in an extra step. In this one, let me get some space. Tan is already isolated in this equation. So tan of 3x, not x, but 3x, has to be equal to the square root of 3. And then the question is, what's x? So we got a couple of things to do here. First of all, just solve it for 3x. So tan of 3x has to be equal to the square root of 3. How do I know when that happens? Well, I know it's going to be a solution that I've learned. So on my unit circle, a square root of 3 only shows up in the multiples of pi over 6. If a square root of 3 is showing up, that means that it's root 3 over 2 and 1 over 2. Now remember that tan is sine over cosine. And the root 3 here we could think of as root 3 over 1, so that I have a fraction. So if you think about it this way, you'd say, well, the root 3 goes with the sine, and the 1 goes with the cosine. Now imagine if you just divide the top and the bottom of that fraction both by 2. Then I can see, okay, tan is going to be equal to root 3 if sine is equal to root 3 over 2, cosine is equal to 1/2. So my coordinate would look like this. There's one catch, because I did the division and it comes out positive. My answer is positive root 3. How do I know if that came from positive divided by positive or negative divided by negative? So another way to get the exact same thing would be if cosine was -1/2 and sine was also negative. So these are the two spots that I'm interested in on my unit circle. That comes from the multiples of pi over 6. So let's try to find those. In my first case, positive, positive, that's in the first quadrant. X is smaller than y because x is the 1/2. So x is smaller than y, so it's sort of here. In the second case, -1/2, negative root 3 over 2, that would be the third quadrant for them both to be negative. And again, x is smaller than y, so I go horizontally, not as much as I go down vertically. So that's going to be over here. Now we just have to figure out what are those. So 0, 1 pi over 6, 2 pi over 6, 3, 4, 5, 6 pi over 6, 7, and then here I get to 8 pi over 6. So those are the spots. There's one more catch to this particular problem. We're not out of the woods just yet, because we're trying to solve for x, but it's tan of 3x that would have given us root 3. Also, the region that we're supposed to be looking at is only from 0 to pi. So 0 to pi is just this top half here. So the numbers I'm solving for right now are values of 3x. So one value of 3x would be 2 pi on 6. Another one would be 8 pi on 6, or of course you can reduce those. But to get to x, I'm going to have to divide by 3. So when I divide by 3, the angles that I get are going to look quite different. I'm going to get 2 pi divided by 18, 8 pi divided by 18, or we can clean that up. So pi over 9, and 4 pi over 9. But how do I know if there are any more solutions that are in my region from 0 to pi? These ones so far, they are in my region from 0 to pi, because remember that pi would be 9 pi over 9. So we don't want to go past 9 pi over 9. So I need to check, are there any more solutions that I would reach before I get to 9 pi over 9? To do that, look at the two positions where you found solutions. So let me clean up a little bit here. At 2 pi over 6, go another turn around the circle and figure out what would be the next solution that lands you at that point. So 2 pi over 6 is at this position here. I'm going to get to that position again and find another solution. If I keep counting around, so after 8 pi over 6, I count 9, 10, 11, 12, 13, and then 14 pi over 6. That would give me another good solution. And then when I solve, oops, sorry, I wrote that in the wrong spot. 14 pi over 6 would be up here. Or we can reduce that, of course, but we'll do it after. So 14 pi over 6, I'll divide by 3 and get 14 pi over 18. And then if I reduce it, I get 7 pi over 9. That's before 9 pi over 9, so it's another good solution. Basically, you keep doing this until you go past your interval, and that's when you know you've caught everything. So if I do the same thing for 8 pi on 6, when am I going to get to this position again? Well, I know that 14 pi over 6 got me up here, so let's keep counting. 15, 16, 17, 18, 19, 20. 20 pi on 6 would bring me back to the same position as 8 pi on 6. That would also be a solution. That would be for 3x, so divide by 3. That's 20 pi on 18. And if I reduce, I get 10 pi on 9. Okay, but that's not in my interval, because the question is only asking for answers between 0 and pi. 10 pi on 9 is bigger than pi, so we stop here. So there are 3 good solutions in my interval: pi over 9, 4 pi over 9, and 7 pi over 9. This is what you need to do when you're solving a trigonometric equation, but the argument, what's inside the function, is not just x or theta. You have to first solve for this expression, and then afterwards solve for x, keeping track of the interval that they asked you about. So 5e is the same idea as D was, in that first we're going to find the answer for the original argument, the x minus pi over 3, and then we'll figure out what that means for x. Notice that this time we have kind of a more unusual region that we're looking for solutions in. It's from negative pi on 2 until positive pi on 2. What would that mean? Well, we know pi over 2 is up here, and negative pi over 2 would mean we travel the same distance but in the opposite direction. So negative pi over 2 would be represented down here on the unit circle. We're looking for stuff in this region here. So let's first isolate our trig function. We have 6 cosecant of x minus pi over 3 needs to equal 12. I'll divide both sides by 6. So it needs to equal 2. Now cosecant we know is 1 over sine, so 1 over sine of x minus pi over 3 needs to equal 2. That means that sine of x minus pi over 3 needs to be 1/2. That's what it boils down to. So where does that happen? Well, sine is the y value, 1/2 is the smaller of our pair for multiples of pi on 6. So y needs to be positive 1/2. That's going to happen over here on my unit circle and over here. So this one would be pi over 6, and then we'd have 2 pi over 6, 3 pi over 6, 4, 5 pi over 6 would be right here. However, we have to respect our region. So that means that we might have to find some other values to go along with these ones. If I continue going all around the circle, 5, 6, 7, 8, 9, 10, 11, 12, 13 pi over 6 would be another solution. I can keep going. 14, 15, 16, 17 pi on 6 would be another solution. But I'm actually allowing negative angles this time because my region starts at negative pi on 2. So let's try counting the other way also. So if I start at 0 and I count in the negative direction, I could have -1, -2, -3, -4, -5, -6, -7, and that brings me back to this solution. So -7 pi on 6 would be another option. Keep going. -8, -9, -10, -11. So -11 pi on 6 would be another solution. So these would all work as values for our original argument, in other words, as values for x minus pi on 3. So x minus pi on 3 could be pi on 6, it could be 5 pi on 6, it could be 13 pi on 6, 17 pi on 6. It could also be some smaller things. So in the negatives, we found that it could be -11. -7 pi on 6 would come before, and -11 pi on 6. And of course, there are infinitely many other ones if we keep going round and round the circle in either the negative or positive direction. But let's start with this and see where it gets us. So if x minus pi over 3 is equal to these numbers, I need to now solve for x. So it's going to be good to note again that pi over 3 is 2 pi on 6. Which would be equal to any of these values. So to solve for x, I would be adding 2 pi to each of these. Sorry, I would be adding 2 pi over 6 to each of these. So let me just go through and do that. -11 pi on 6 would become -9 pi on 6. -7 pi on 6 would become -5 pi on 6. I'm adding 2 pi on 6 to everything. So pi on 6 would become 3 pi on 6, then 7 pi on 6. At some point, you're going to notice that you're not in your region, so you can stop. You don't have to do all of them. Let me draw my region again. I'm only interested in solutions from -pi on 2 until +pi on 2. Let me break that into sections according to multiples of pi on 6, since my solutions are written that way. So I can write this as I have pi on 6 would be acceptable, here 2 pi on 6 would be acceptable, and it ends at pi on 2, which is 3 pi on 6. In negatives, -pi on 6 would be okay, -2 pi on 6 would be okay, -3 pi on 6 would be okay, and that's where it ends. I'm doing that so I can easily identify what are my allowed solutions. So going back to my list, I can see that -9 pi on 6 is not in my region. It is too far into the negatives. Same thing for -5 pi on 6. My region ends at -3 pi on 6. So those would not be included. +3 pi on 6 is a good solution. It's right on the boundary of my region, so I can keep that one. And then 7 pi on 6 is past my region, so I would take that one out. So there's actually only one solution that's in my region. Just make some space here. The only solution in our region is 3 pi on 6, or it's much better to give your answer as pi over 2 by reducing the fraction. All right, F is a little bit of a break. It's not as bad as E, and it's not as bad as G is going to be either. So F is a pretty quick one, actually. We have sine squared. Remember that that's the same thing as sine all squared, and that needs to equal 1/2. We can take the square root on both sides. That would mean sine of x needs to equal plus or minus square root of 1/2, which we can say is plus or minus square root of 1, which is 1, and square root of 2. This, if you don't recognize it as a value on your trig circle, it's something that you should recognize. It's just an alternate way of writing root 2 over 2. You can see that by rationalizing. So if I multiply the top and the bottom by the square root of 2, I get plus or minus square root of 2 over root 2 times root 2, which is 2. So these are famous numbers from our pi on 4 unit circle. So We know that they occur in these 4 positions. And we want y sine to be equal to either root 2 over 2 or negative root 2 over 2. Well, that's all 4 of these spots. Since it's allowed to be both positive and negative, we'll take the ones above the x-axis and below. So that would happen at pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. Or, you know, you could keep going around the circle, or you could go into the negatives, but our region is only from 0 to 2 pi in this question. So it's just those 4 answers. X can be pi on 4, 3 pi on 4, 5 pi on 4, or 7 pi on 4. And we're done. The last one is 5G. This one is on here to remind you of a particular technique you should have seen in high school that will show up every once in a little while. This expression is quite different from the other ones in that it wouldn't be simple to isolate for our trig function. So that is its own kind of little project. How do I solve for cosine if there's a sine around? Or how do I solve for sine if there's a cosine? The trick here is to notice that you have kind of a quadratic equation in that you have squares, and then you also have the power of 1. So if I only had cosines, or if I only had sine, I would be able to treat this like a quadratic of the type ax squared plus bx plus c, and I could use factoring techniques or other techniques for solving a quadratic. I can't do that yet because I have a mixture of sine and cosine. So in a question like this, you need to convert so that everything is cosine or everything is sine. You're going to do that using our famous Pythagorean identity, sine squared plus cos squared equals 1, which also means that sine squared is equal to 1 minus cos squared, and cos squared is equal to 1 minus sine squared. In this question, it doesn't make sense to get rid of the cosine using this method, because you could get rid of the cosine squared, but you'd still be left with these other cosines that you can't get rid of that way. It makes more sense to use this identity to get rid of the sine squared in your equation. So that's the first thing I'm going to do. Sine squared will become 1 minus cos squared, thanks to my Pythagorean identity. Everything else will stay for now. Now let me open up my bracket. And this is basically a quadratic equation. Maybe it doesn't look that way right now, but if you were to take all of the cosines in this equation and replace them with some other letter, let's say if I said y is equal to cos x, then y squared would be equal to cos squared of x. Then this equation that I have here would be 1 minus y squared minus 2y is equal to y squared minus y. So do you know how to solve an equation like that one? If you remember, what you should do first is put everything to one side of the equation so that it's set equal to 0. So I'm going to move everything to the right-hand side. I have cos squared plus cos squared will give me 2 cos squared. I have plus 2 cosine minus cosine will give me plus cosine. And I have minus 1. And if this is too fast for you, please do take the time to do that step on your own. You should always have pen and paper with you or pencil and paper with you when you're watching a math video. So if I skip a step and you want to do it, please pause and do that step. But anyhow, this is where you would get, which is equivalent, if you prefer to write it with y's, then it's just the same thing as this. It's basically 2y squared plus y minus 1. Now we can check if this factors. It does. I'm not going to go into all the details here because there are some other videos about factoring that you can check out on our website if you need to review your factoring. All I'll say is that to me, it's pretty clear that if this were to factor, then it's going to be 2 cosine times 1 cosine, because that's the only way to get 2 cos squared with nice numbers. And in the back, it needs to multiply to -1. So that would have to be a positive 1 times a negative 1. I don't really have a lot of options. So I know it's something like this. And then I just have to play around a little bit to figure out which one is positive, which one is negative, so that when I expand, I would get plus cos in the middle. And it's pretty clear to me that it has to be like this. Or again, if you want to work just with y at first so that you don't get confused, you can do that. And this is the factoring that you would get. Once you have that, you have a product of two things that equals 0. The only way to have two things that you multiply and it gives 0 is if one of them was 0 to begin with. That allows us to solve the equation. It only works because it's set equal to 0. It wouldn't work if it was set equal to 5 or something like that. So the only way to get these two things multiplied and it ends up equaling 0 is if either 2 cos minus 1 equals 0, or if cos plus 1 equals 0. So I can solve each of those now. Now it's starting to look more like part A, something a bit more straightforward. It's just that I get two cases that I have to address. And I'm going to be solving this on the region from 0 to 2 pi. So at this point, the tricky part is over. The new stuff is over. So if you got stuck on this problem and you want to pick it up from here, you should be able to finish it. You're now just looking on one regular turn of the unit circle for the solutions for cos x equaling 1/2 or cos of x equaling -1. So you might want to pause here and try that out for the practice. If not, I will continue. Cosine is the x value. If it's positive 1/2, that's over here. It's the smaller number from our pi over 6 set. So that would be these two positions. If I count around to find what those are, I get 0, 1, 2, and 3, 4, 5, 6, 7, 8, 9, 10. So 2 pi on 6 and 10 pi on 6, which I can reduce. Pi on 3 and 5 pi on 3. That's for my first equation. Second equation, cosine equals -1. So my x value would have to equal -1. That only happens in one place. That happens right here on the negative x-axis. So that I know is the angle pi. So altogether, I get three solutions. X can be equal to pi over 6, or pi, or, oh, sorry, I wrote pi over 6, I meant pi over 3. X can be pi over 3, or pi, or 5 pi over 3. That concludes it. I have to tell you that especially in number 5, this got pretty challenging. So if you can do all of this, you are in really good shape for your calculus class. Congratulations.